Hello and welcome to lab number 11. The title of this lab is Measuring Laser Beam Diameter and Divergence. In the previous labs we manipulated with the light. We performed a whole bunch of different experiments where we observed the reflection and the refraction, etc. And in order to perform those experiments we used a light source. In our case we used our red laser diode module. So in this lab we are shifting our focus to the light source. So we want to learn a little bit about our laser diode that we have been using in the previous labs. Lasers are an important optical component that have a whole bunch of different properties or output characteristics. Among different output characteristics of a laser that are going to be used to compare different types of lasers, the most important one would be the intensity of the laser as well as laser beam diameter and divergence. So in this lab we are going to learn a little bit about this later one, called laser beam divergence. So we're going to see that lasers are producing laser beams. So the laser beam is leaving the aperture of the laser and it is changing its width. In other words, it's diverging. So if you're measuring the cross section of the laser beam at different locations away from the aperture of the laser, you're going to see that the laser beam diameter is going to be different. It's going to expand, it's going to start increasing, and divergence is that important property of the laser that is telling us how much the diameter of the laser beam has changed as the beam continued propagating away from the aperture of the laser. So there is going to be the formula that we are going to use, and then we are also going to perform a few measurements in order to quantify the divergence of our laser diode module that we have been using in this set of experiments. So at the end of this lab you're going to learn how to define a laser beam divergence. And then you're also going to learn an important practical skill, which is going to be the measurement of the laser beam divergence. So we're going to set up an experiment in which we are going to be taking a few measurements, and based on those measurements we are going to calculate the laser beam divergence for the laser that we are using. The equipment that we are going to use in this lab consists of a laser diode module, a laser holder. Here we have two plastic lens holders that we are going to use to hold our back screen. We are going to need measuring tape, a protractor with a ruler, and finally pencil and a white sheet of paper. In this first measurement, the laser has been positioned at the distance of 15 centimeters away from the screen, and we turn on our laser, and as you can see the laser is producing the laser beam that's hitting the screen, and it's leaving this mark here. That's our reflection from our red laser diode. And in order to perform the full measurement and calculation of the beam divergence and the beam diameter, we are going to trace the reflection on the back screen and then perform the necessary calculations. So what I'm going to do here, I'm going to use the pencil and I'm going to go and mark the reflection on the screen. We have now positioned our laser at a distance 140 centimeters away from the screen. And at this distance of 140 centimeters away from the screen, we are going to measure the diameter of our laser beam at the back screen. In order to do that, we are going to mark around the reflection that our laser pointer is leaving on the back screen. Okay, let's now perform the calculations. So the first thing that we want to do is we want to measure the laser beam diameter based on the marked dots that we have on our back screen sheet of paper that has been positioned right now on my workbench. So the first that I'm going to do is I'm going to measure these two beam diameters. So it looks like the first beam diameter was about 5 millimeters, so D1 is equal to 5 millimeters. We measured this beam diameter when the laser was at the distance L1 equal to 15 centimeters. And then at the distance L2 from the back screen to the aperture of the laser equal to 140 centimeter. We are measuring about 1, 2, 3, 4, 5, 6 millimeters. So D2 is equal to 6 millimeters. At this point, it's important to observe as well that the footprints that the laser beam left on the white screen are not perfectly circular, but rather in elliptical shape. That's an important property of a laser diode. So remember that the laser diodes have elliptical shape of the laser beam, as opposed to some other lasers that would have more of a circular shape. There's an important output parameter that characterizes the shape of the laser beam, so-called ellipticity. And that ellipticity is, in this case, going to be much larger than 1, because the width of the beam in a vertical direction relative to the width of the beam in a horizontal direction is significantly different. Now that we have our distances and our diameters, we can also here convert to the same unit. So 1 centimeter has 10 millimeters, so we can convert 15 centimeters into 150 millimeters, and then same here, we can convert 140 centimeters into 1,400 millimeters. So the formula to calculate the beam divergence is given here. The beam divergence theta is equal to D2 minus D1 over L2 minus L1. So we are going to substitute for the values that we just measured. So for D2 we have 6 millimeters, minus D1 being 5 millimeters, over L2 being 1,400 millimeters, minus L1 being 150 millimeters. So if you subtract the values in the numerator and denominator, in the numerator you're going to have 1 millimeter over 1,250 millimeters in a denominator. And as you can see, these units cancel out. And then you're going to do on your calculator 1 over 1250 equal to 0.0008. And the unit that we are going to use here are the radians. You can further convert this into milliradians. So this laser has a beam divergence of 0.8 millirad or milliradians. Now the question is if this laser diverges significantly or not. So here we are dealing with the radians. So what you can do if you're more comfortable with the degrees as a unit of an angle, so we can convert the radians into degrees. So we know that 2 pi radians is equal to 360 degrees full circle. So 2 pi of radians is equal to 360 degrees. So our beam divergence theta is going to be equal to 0.0008 radians, and then you can multiply it by 360 degrees over 2 pi radians. So you can cancel radians and radians here, and then if you do the math, so 0.0008 times 360 divided by 2 and divided by 3.14 gives you about 0.046 degrees. So divergence of this laser is only 0.046 degrees, so very, very, very barely diverging type of a laser beam. So So as you can see, we have calculated a very small divergence in the case of our laser diode. It's important to mention that laser diodes, they have a pretty significant divergence, so that's the laser that diverges the beam significantly. And the question is why we are getting such a small divergence. Explanation for that is because this laser that we are using is actually having a smaller lens that's been installed here in front of the actual laser diode. So that lens that's inside of this laser module is collimating the beam. Collimating the beam collimation means that the lens is reducing the divergence of the laser beam significantly to the point where we have a very small divergence as we observed through our calculations. So once more, laser diode is characterized by a significant beam divergence of 20-30 degrees or more. However, in our case of our laser diode module, we don't have just the laser diode, but we also have a small lens here that's collimating the beam, meaning reducing this significant divergence that's being produced by the laser diode, so that whatever comes out of the aperture of the laser has a very small divergence as we observed in our calculations.